Okay, well, it's 6 o'clock, or it's Eastern time here in the US. And so I think we're going to go ahead and get started with our first talk. So Laura Hayes is a postdoc at NASA Goddard Space Flight Center here in Washington, DC, as well as a frequent contributor to SunPy, and a maintainer of several of the sub packages within the core repo, and a participant in the community as well. So she's going to tell us about the SunPy package, what it is, and give us some updates on our 1.0 release that we've had in the past year. So go ahead, Laura.
Cool, thanks, Will. So just to make sure everyone can see my screen. Yeah, we're good.
Yes.
Yes, cool, okay. So yeah, thanks. First of all, thanks to the PyAstro organizers for going ahead with PyAstro, which is great. I am, of course, sad to not get the opportunity to fly back to Dublin. But anyway, this is great. So yeah, as Will said, my name is Laura. I'm a postdoc at NASA Goddard Space Flight Center. But I'm here today just to fly the flag of SunPy. I mean, I'm in no way SunPy as a whole. I mean, SunPy is a community. It's been developed by many, many different people across the world. So this is just me flying the flag of all the work that has been done within the community. So yeah, what is SunPy? I guess it is a community developed free and open source solar data analysis software environment for Python, excuse me. And what I'll talk about today is we'll mention kind of where SunPy is at the moment, where did it come from, what's in 1.0, and what's for the future. So you can check us out on our website, sunpy.org, or on our GitHub repo. So yeah, so I thought maybe to begin, I might just give, I'm aware that there might be astrophysicists as well as solar physicists here. What are the needs for a solar physicist in regards to software? So what do solar physicists do, and what do we need? So essentially solar physicists, as you might in the name describes, we study the sun. And in this way, we kind of study solar events, things like solar flares and coronal mass ejections, which are explosions off the surface of the sun. We study the sun as a star, kind of putting it in a place of kind of solar and stellar observations. Of course, space weather is a huge aspect of solar physics. How do these solar events impact the near Earth environment? And then again, the sun being a very close star nearby, it essentially is a plasma lab in the sky. So we can do an awful lot of plasma physics. And one of the nice things about the sun in astrophysics is it's really, really close, and we can make lots and lots of observations of it and really detailed measurements. And we do this by both space and ground-based instruments. So we have lots of different space-based instruments and lots of different ground-based instruments. And so we have lots and lots of data. And because it is so close, it's easier to kind of download, link a lot of this data. And this is just an example over here to the right, of kind of the Heliophysics System Observatory of NASA. So this is just showing kind of even just some of the instruments that solar physicists use to kind of study the sun, including some of the new ones in Solar Orbiter and Solar Pro Plus, and then some of the old ones such as SOHO and RESI and SDO. And just to give you an idea, SDO is the instrument, AIA on board SDO takes images of the sun in many different wavelengths at really high time resolution. So you're downlinking 1.2 terabytes of data a day. So this is a huge amount of data. And the different types of data we get are images, time series, spectra. And in terms of software, we need a way that we can download this data, how we can read in this data into different standardized formats. How do we deal with different coordinate systems from different observations? For example, you might be kind of looking at multi-wavelength observations from several different ground-based and space-based instruments. How do you kind of put them together into kind of a standardized way to kind of focus on one feature of the sun? How do you make sure that your coordinates are correct and things like that? And of course, with this, then you need to have a way to explore the data and to visualize the data to kind of make scientific ready results. So that's kind of an overview of kind of the data we're kind of dealing with in solar physics and what kind of software we need. We need to have the ability to do these types of things. So where do we stand at the moment and what's available out there? So there's kind of two main packages at the moment, I guess, in which you can analyze solar data from many different instruments. Kind of the past has really seen the development of solar software, which is written in the interactive data language IDL. So this has been around for a very long time. And with that, it's kind of like 2 decades of an awful lot of software, and in particular, instrument-specific software. So specific instrument teams might write software in SolarSoft, which would have kind of the ability to calibrate data and do lots and lots of different things. And it has a huge legacy up there of all the software that has been written over the last while. Again, of course, this has brought a huge amount of software. There's 4 million lines of code, and if you want to download it, it's over 16 gigabytes in size. SolarSoft is open source. It's closed development, so you can't just essentially contribute. If you find a bug, it's difficult to change or find some documentation. And while it's open source, IDL is not open source. You have to pay to have IDL. So that's kind of one downside of it, I guess. And of course, another kind of downside is it's not version controlled. It's not essentially coordinated or organized, and there are a lot of conflicts. So, however, it is kind of a monolithic code base, which has kind of, you can almost do anything you could possibly want in SolarSoft if you wanted to do things in solar physics. So that's kind of where we kind of stand and what's available. And then, of course, there's also SunPy, which is, instead of IDL, it's based on Python. And I'll talk about SunPy in this talk, so I didn't think I'd highlight kind of main features here. But where is the community? Where are we at in using these different software? Kind of who uses what? And I just wanted to point to a really interesting community survey that was led by Monica Barbara and the SunPy team and the SunPy board to kind of survey the community and see what type of computational software they were using in their research. So the study kind of consisted of 13 survey questions that were decided upon by the board and after lots of discussions to understand exactly kind of what solar physicists are using. So 364 people took this survey across 35 countries. And I think this was a really interesting plot because you think that, I mean, maybe you live in a bubble of everybody using Python, but IDL is still very much out there. So as we can see, this is broken down by who uses IDL, who uses Python, and kind of what career progress you're at. So you can see that faculty, staff, and researchers, some more established maybe researchers, are still using IDL in the majority. And then when you go down to students, both undergraduate and graduate students, it kind of seems that Python is becoming the dominant language. However, really, another interesting thing to note here is that a lot of people are using both, including myself. This is what I do. I mean, there is an awful lot of legacy code that is available in SSW, including kind of calibration and functionality and things like that. But just something to keep in mind that compared to astrophysics, I think they did a similar survey and found it was much more skewed towards Python. IDL is still a very common language, which is just kind of interesting. And I'd really recommend anyone to go check out Monica's paper on the survey with all these different results in there. So moving on, so what is SunPy? I guess is the aim of this talk. So what is SunPy? So the SunPy project, the project as a whole, facilitates and promotes the use and development of several community-led, free, and open source data analysis software packages for solar physics based on the scientific Python environment. So that's kind of the project description as a whole. The project is a NumFocus sponsored project, which is kind of nice. And we are also part of the Python and heliophysics community. And the Python heliophysics community's mission is to essentially enable interdisciplinary analysis across all disciplines in heliophysics and adhering to certain kind of code standards. So it's kind of nice that SunPy is involved in this. And the SunPy core package, so the actual kind of core software package of SunPy, is a community-led and open source software package for solar physics. And this kind of aims to kind of get kind of an open, comprehensive data analysis environment that allows researchers to do their research in Python. And the SunPy project kind of facilitates the SunPy core to kind of do that. And the main goals of the SunPy project and the SunPy package could kind of be broken up into two separate things. So the functionality goals is, of course, we want to provide Python tools for solar data analysis, and it's essentially to kind of provide a gateway into the amazing ecosystem that is scientific Python. So it's a way to kind of get your data in and then use what is out there. So this kind of is a little bit different from maybe what's available in SSW IDL, in that it's kind of you're giving kind of a gateway into distributed packages where everything isn't within SunPy, but when you have your data in SunPy, then it opens the gates to using many different packages such as Dask, scikit-learn, all the different packages that are out there. A functionality goal of SunPy again, is to focus on calibrated high-level data. So it's not trying to focus on instrument-specific calibration or anything like that. It's to take data that has been calibrated through kind of an instrument pipeline system, and take this data and then read it into kind of to the Python ecosystem. And again, there's no point in reinventing the wheel. There's an awful lot of mature and maintained code out there that can be leveraged by SunPy, such as AstroPy, and we leverage an awful lot of kind of functionality from them, and many different other kind of packages that we can use, which is great. And also the SunPy project, it kind of has a goal to kind of support other Solr packages, which may be outside the scope of SunPy core. So if you have kind of a specific package that is a little bit niche, but kind of uses SunPy, this can be an affiliated package. And this, again, is supported by the SunPy project. And as well as this functionality goals, we also have kind of a cultural goals as a community. We want to kind of, SunPy isn't just about providing Solr analysis code, it's about having a community. So our goal is kind of have this open source community and be very inclusive. So anyone can contribute, anybody can use it, anybody can report a bug, contribute code, involved in discussions, kind of the path of where SunPy is going. So this is kind of a really nice thing about SunPy. It's also kind of, the SunPy project aims to coordinate development. So again, not having file conflicts, not having two people working on the same thing, when you can coordinate development together to make even better thing. Another kind of cultural goal is to kind of look at making sure you're writing kind of proper code with proper tests and proper code review. So this kind of lives up to the standard of kind of the scientific community. And of course, version control. And this is really important in a scientific community. You want to be able to produce results that are reproducible. So even 5 years ago, if you wrote a paper that used SunPy, you could quote the version and then someone could reproduce your results. So these things are really important culturally to kind of have as a scientific community. And again, another kind of cultural goal is to have standardized and discoverable documentation. So if someone is interested in coming to get involved in SunPy or using SunPy, they can easily find our documentation and they can easily kind of to read it, and it's in a standardized format. So how does SunPy look as an organization? So the SunPy project, or the SunPy organization as it's also known, is kind of modeled after a non-profit organization. So this is kind of the governance that it holds. So if we kind of go around the circle here, we can kind of begin at the SunPy board, and this kind of leads the development or the kind of where SunPy is going. And it consists of up to 10 people. And yeah, it guides the directions of SunPy project. And it does this by voting on SunPy enhancement proposals, similar to the Python enhancement proposals in Python. And the idea here is that anybody can propose a SunPy enhancement proposal, and then it's discussed amongst the community, and then the SunPy project or the SunPy board then votes on this. And again, yeah, anyone can propose. An example of a recent one is that a SunPy enhancement proposal to include AstroPy time throughout the stack. So things like that, kind of big changes to SunPy or the direction of SunPy are brought through the SunPy enhancement proposal. And from the board, we have kind of then the lead developer. And the lead developer, everyone probably knows, is Stuart Mumford at the moment. And this lead developer then leads the kind of core team to kind of work on the guiding direction of the SunPy project and the affiliated packages. And then, of course, there's a deputy leader, because it's a hard job. You need to have a few people, which is Will Barnes at the moment. And then we have sub-package maintainers. So these are people that kind of help maintain the sub-packages within SunPy to kind of assist the lead developer and the deputy developer with all these sub-package maintainers. So for example, if someone makes a PR to a certain sub-package, the maintainer will review that code or kind of assist in this kind of development of SunPy in the future. And then, of course, we have community developers. Anybody can develop or contribute code to SunPy. And most importantly, I guess we have our users. And our users don't need to necessarily develop code. They can report bugs, ask for what they want, and things like that. We have community roles, which includes kind of a release manager and a community manager and things like this. And over the years, we've had lots of really good students from summer codes such as Google Summer Code and UC Summer Code. So this is the SunPy community kind of in a snapshot, and the organization of it. And how do you contribute to SunPy? What does this look like at the moment? As I said, we kind of try to have this open source, open community that anybody can contribute, so anyone can. However, this doesn't mean you can just have some code that you can just push straight to our repo. We have some guidelines in place to make sure that the code quality is met. So they're kind of like 4 main things that are checked. So if you want to contribute code, there is a certain style guide. So the code must kind of comply with kind of the standard guides that would be in kind of the Python standards of writing code, including documentation. Any kind of new features require documentation, the kind of the usual code comments and doc strings. And if it is a big feature, we would request that. Examples are kind of given with it, provided with it for our example gallery. All our code again is tested. So if you write new code, you have to write a unit test to kind of go with this to make sure that the functionality is covered and it doesn't break something else within SunPy. And then finally, it has to be within scope. So we kind of want to make sure that it's within the scope and kind of the path of SunPy is going down. And code is always reviewed. So it's reviewed by at least 2 members of the development community, just to make sure that everything is okay. However, this might seem like a lot, but if you are a newcomer, I would highly recommend to even just come with your code as it is. And the community is really, really welcoming. I can tell you this as someone who only contributed within the last year as a first contributor to SunPy. So lots of assistance are given to newcomers and oldcomers who have forgotten how to pass all the tests and things like that. And then on GitHub, where SunPy lives, there are lots of different automated tests, which is nice to kind of keep things in place. So where is SunPy now? What is the status of SunPy? So just to kind of give a brief background, it was officially founded in March 2014. However, the SunPy package actually began in March 2011, so almost 9 years ago now, which is kind of crazy. This has been a very exciting year, well, late last year, where the first stable release of SunPy happened, which is very exciting. We're now on SunPy 1.1. So what this means is that we consider the API within SunPy to now be stable, fully stable, which is good. We now have kind of a new release schedule. So before it might have been a little bit ad hoc. Now we have a release schedule which will happen twice per year. At the moment, there's over 50,000 lines of code, and this includes comments and doc strings and things like that. And as of today, there's 134 unique contributors, which is actually an awful lot of contributors for a package of its size, which is kind of neat. With 1.0, we saw kind of the publishing of a paper and code, both within the Astrophysical Journal and in JOSS, so the Journal of Open Source Software, in which our code was also reviewed, which is kind of cool. So this is kind of some nice plots to kind of show kind of the status of SunPy up to 1.0. So we can see the lines of code has increased as a function of time, which is always what you should expect, except for what happened with just before 1.0. And this was just due to a major tidy up for the first stable release. An awful lot of kind of legacy code and code that was lying around was taken away. So I think over 3,000 lines of code was taken away with the 1.0 release. You can see lots of contributors, which is good. However, on the right-hand side, the number of contributors versus the number of commits, of course, we have a lot of contributors, but however, the slope is quite steep. So what this means is that there are a few contributors like adding most of the commits. So what we really want to do in the future is to try get the users and get people that are contributing. We want to essentially flatten this curve. So another curve we want to see flattening. Which would be good, because you want kind of a healthy community that many people are involved and many people are essentially we're not dependent on a few people to kind of keep the upkeep of SunPy. So SunPy 1.0. So I'll just sort of give an overview and some of the highlights, and then I'm going to talk through some of kind of the main points of SunPy, the main kind of aspects of what SunPy can actually do. So kind of the headline core changes of what happened in SunPy 1.0. As I mentioned before, there was a major cleanup of core. So this was kind of getting rid of a lot of kind of legacy code that was lying around, or taking things out that weren't kind of being used or kind of within the scope of SunPy. SunPy 1.0 now has improved download capabilities using PAR5, which is really nice. So it can do kind of like multi-file downloads in parallel. We have one of the coolest things, and I'll show some really nice examples of this, is improved coordinate functionality. So a lot of Sun-specific coordinate frames, and we have now a whole transformation stack of how you can kind of move within different coordinate frames and kind of fit into the full AstroPy stack, which is really, really nice. We have full adoption of AstroPy time. So before it was based on date time, but now it's throughout the SunPy, it's now AstroPy time. And we now also have a logging system, which you can use rather than printing out just an error. And you can choose which messages to show, which to capture, and which kind of send to a file, which is nice. So just kind of, I'll go through kind of the main kind of highlights of SunPy now. I guess if you're kind of doing solar data analysis, the first thing you would like to do is to retrieve some data. And SunPy kind of offers this through the sunpy.net subpackage, and in particularly Fido. So Fido, what it is a unified API for searching and downloading solar data from various search engines and data sources. So when you have solar observations, whether it be ground-based or space-based, a lot of these are hosted in many different ways. They can be hosted on the VSO, they can be hosted on JSOC, or they can be hosted on their own web servers, such as HTTPS or FTP. So Fido has a really nice way of, regardless of the underlying client, you can search for your data and it will return it as something that you can then download, which is nice. So here's an example of using Fido just to kind of search over some time and search for using a specific instrument, which is XRS. We can see you search, you find your results. So we can see there's kind of 3 files here, and then you can use fido.fetch to download your data. So this is a really nice way and kind of a first step that you can get access to your data. Then once you have your data, you want to have a way that you can contain it. And how do you read it in? So at the moment, SunPy provides kind of an interface to standardize reading in different types of solar data from many different instruments and missions. At the moment, there's 2 types of data containers. There's time series, which holds 1D temporal data, and map, which holds 2D coordinate aware image data. So on the left-hand side, you can see a nice image of time series data using X-ray observations, and on the right, we can see an image of the sun using SDO AIA, an extreme ultraviolet wavelength. So what's really nice about this is, regardless of, again, the kind of what file type it is, SunPy provides kind of a way it will take the file, it will recognize what type of file it is, it will populate the necessary metadata keyword arguments within time series and map, and generate it into then a standard form that the user is given, whether it be time series or be map. So just to kind of give kind of more of an overview of time series, as I said, it's for 1D temporal data. And you could just argue, well, why don't you use just a pandas data frame or something like that? And pandas data frame is used underneath. However, what time series is nice is that it, again, doesn't matter what type of file type it is, if it's a FIT file, if it's a CSV file, it will recognize where it came from and kind of populate the metadata container, which can hold that information about the metadata of the instrument, whether it be exposure time, what instrument it was, and things like that. And again, if we look at the metadata, it corresponds to specific times and columns. And what this allows then is for you to kind of, in a smart way, like concatenate time series together or truncate time series together, or resample. And this can be done then for different instruments and things like that. And here's just a little snapshot of looking at time series. It's just, you can kind of, all you do is you give the time series object a file, and then it reads in from this file all the metadata and all the data. And you can have then, it has associated units with it, so AstroPy units, which is nice, and watts per meter squared. And then it also contains the meta information. So everything you might need that would have been in the FITS header, for example. So that's time series. It's quite nice. I think it is now supported for 6 different instruments. And this can be easily upgraded if you want to include, for example, a new instrument that is then supported in time series. And there are easy ways to do this to contribute to SunPy. And then map, I guess, is kind of the perhaps most developed container of SunPy. And what it is essentially a data container to interface with coordinate aware 2D images. So here again is an example of AIA image. And And as it is coordinate aware, then you can use the coordinate stack to then plot things within the WCS axes. So here, for example, you can get the flare location in whatever kind of coordinate system you like, but you can then plot it onto, this is helioprojective coordinate system here. And then there's loads of different functionality. For example, if you wanted to crop an image within the square and plot it, and you can plot a color bar. So this is kind of a different, so this is map overall. So I think kind of the newest thing within SunPy 1.0 is the kind of great development that went on with the SunPy coordinates module. So SunPy coordinates is the subpackage that has the functionality to represent and transform coordinates used in solar physics. So it has developed an awful lot of kind of sun-centered data frames that are used within SunPy and are used within instrument observations, for example. And here's kind of a spaghetti plot of how it fits into the AstroPy functionality. So within the red are all the kind of coordinate frames that are provided within SunPy. So the ones on the left-hand side are kind of the sun-centric ones. So most of the solar data that we get from instruments might be in these type of coordinate frames, or we can kind of transform them between different coordinate frames. And each of the arrows shows how you might do that. What's nice as well is then you can easily then, if you wanted to use different frames within AstroPy, that's easy to do, or vice versa. And we also have some Earth-centric coordinate frames as well, which is used within the heliophysics community and some solar cases. So I thought now maybe I'd just go through some examples of kind of the solar coordinates module used within kind of different aspects of SunPy. So here are some neat examples of using kind of map together with the coordinates module. So the image here on the left is a coronagraph image of the sun, of the solar corona, and this is observed with stereo A of the instrument core 2. And so you can see where this white circle in the middle, that's where the sun should be, but it's blocked out as it's a coronagraph. And each of the circles represent predicted positions of the stars from Gaia, which is kind of cool. So you can read in a file that has predicted positions of the stars in a certain format, and then we can plot it into helioprojective coordinate system as we see here. And in the square box, you can get the predicted position of Mars. So it's kind of a really nice way that you can work with solar data and then how this feeds into the larger stack that is AstroPy and lots of different astrophysics coordinate systems. And then on the right at the top, we have kind of magnetic field lines traced out from force field extrapolation, which can then be plotted on top of an AIA image to kind of look at where the loops are. And below here we have the Venus transit. So this is Venus crossing the surface of the sun as seen with AIA. And then we can plot with that white X mark, we can kind of search for the predicted position of Venus and then plot it within the same frame. And then moving on, if you want to kind of look at how you can transform images of the sun into different kind of projections and kind of work together with different spacecraft. And this is really important going into the future. So here we're showing an example of AIA, which is kind of located basically at Earth, taking images of the sun, and together with stereo A and B. So these are two separate spacecraft that are kind of flying around the sun. So we have stereo A and stereo B. So we're seeing three different perspectives of the sun. And at this certain time, the way they are orientated, you can essentially see every aspect of the sun, or every kind of part of the sun. So within SunPy now, what you can do using the really nice coordinate stack is you can create a full map of the sun using observations from these three things. So to get the positions of the satellite, we can kind of, from the FITS headers of the images themselves, we can get the positions plotted in reference to the sun and to the Earth, get the data, read them into maps, and then using reproject, which is an AstroPy affiliated package, create this map in heliographic Stonyhurst of the full sun, which is really, really nice. And if you want to check this out, it's in our example gallery. So just to kind of use this. Another kind of really important part of coordinates and what we can do within SunPy at the moment is, again, when you're using two separate spacecraft that are looking at two parts of the sun, and you wanted to find a region of interest. So again, we can plot the positions here on the right of the sun, of AIA and stereo A. Both are looking in extreme ultraviolet wavelengths. And if we look at the region in the white box from AIA, we can then find the coordinates of that white box, transfer them into the coordinates of that the coordinate system of stereo A, find out where exactly that is in stereo A, and then we can kind of focus on which loops are which, and see what loop we're seeing in AIA and how does that compare to what we see with stereo A. So I mean, there's so much you can do with this, and this is really important going forward, especially for new observations with Solar Orbiter and Solar Parker Probe, as these won't be kind of looking at Earth, these will be going into very close distances towards the sun and taking observations as they're flying very quickly towards the sun. So it's really important to have this stack available looking forward into the future. So again, I really recommend checking out our example gallery. And talking about that, one of the kind of major things that was also done in SunPy 1.0 was a major revamp of the documentation in the example gallery. So here's just a screenshot of our user guide on our documentation. It's really nice. I would really recommend anyone interested to go and check it out. And particularly the example gallery. So here again is a screenshot of maybe different examples that are done with the map object. So for example, rotating a map, resampling a map. And when you click into this, you can go and try it out. It kind of gives all the code, it describes what it's doing. And you can also download the full version as a Python script or a Jupyter notebook. So I think this is kind of some of the power that we have within SunPy at the moment, is you want to be able to tell the community as much as you can about what the functionality is within it. So yeah, definitely go check that out. And if there's something that you would like to see in the example gallery, either you can provide it yourself, which is fantastic, or you can raise an issue and be like, I'd love to see an example of how to do X in SunPy. So as well as SunPy core, we also have affiliated packages, which I mentioned earlier. And the affiliated packages of SunPy are essentially a way to kind of foster collaboration and coordination and kind of reuse project support that within SunPy. And what the affiliated packages are essentially packages that build upon the functionality of SunPy and provide useful tools to the solar physics community that might not necessarily be required within SunPy core. So these are kind of four main ones that I'll just quickly discuss. NDCube, which is really powerful. I'll talk about that some more in a minute. But essentially, it's a base package for multi-dimensional coordinate-aware data arrays, n-dimensional data arrays. We also have DRMS, which is a way to kind of access HMI data, AIA data, MDI data with Python, which is really nice. Radio spectra, so this kind of tries to provide some support for radio spectra, mainly using the Callisto network. And then, of course, we have IRIS-Pi, which is now kind of moved actually to be called SunRaster. So before it was a package for handling data from the IRIS satellite, but now it is more generalized to kind of using any split spectrograph data can be used now within SunRaster. And if you're interested in affiliated packages, I'd recommend checking out Monica Barbara's Hack Day idea for kind of a review process of how do you become an affiliated package. We have some standards at the moment, but we would like to kind of discuss this more about what it means to be an affiliated package and what is the kind of standards that we adhere to at SunPy. And then another thing about affiliated packages is, as we said, SunPy, its functionality goals is to kind of look at high-level data, so data that's already been calibrated. So for example, an instrument team that does not have an affiliated or any kind of Python package at the moment might want to begin as an affiliated package to develop things within the kind of ecosystem of SunPy and the support of SunPy, and then where this can then contain the different type of calibration routines or things like that. So just a brief chat about NDCube. I thought I'd mention this quickly. So NDCube is one of the SunPy affiliated packages. It is really powerful, and what it does, it provides a base class of ND astronomical and solar data. It's based on ND data of AstroPy. That's its base class, and it is a way to kind of deal with WCS axes essentially, so coordinate-aware astronomical and solar data. And it provides functionality of like really powerful slicing operations, different types of coordinate transformations, different data masks, different types of uncertainties, all contained within a cube. And then it has an awful lot of visualization tools, which are really nice if you're trying to look at n-dimensional data. And why I mention this is that it is the next planned base class for math in SunPy 3.0. And it can be used for many different base classes and be a kind of a parent for an awful lot of different types of data structures, whether it be spectra, whether it be images, So I would recommend, if you're interested in this, talking to the lead developer, Danny Ryan. I think he should be around during the hack days. And this is kind of an overview of kind of what an NDCube looks like. So of course you have your data, and then you have associated metadata, associated units, and then really importantly, it has this associated WCS coordinate transformations. So this kind of is really nice. You can have uncertainties and masks and all different types of things. So again, yeah, definitely talk to Danny Ryan or to myself or to Stuart or to anyone if you're interested in looking into this further. So I've just kind of talked about SunPy and SunPy 1.0, but where are we going in the future and what is our roadmap? As I mentioned, there are 2 new releases now planned per year. So SunPy 2.0 is coming up in May. It's coming up very fast. So keep an eye out for that. The kind of future plan for SunPy at the moment is to use NDCube for maps. So one of the main kind of motivations for doing this is for times when you have like n-dimensional map data. And at the moment, map doesn't really support this. So NDCube will be a really nice way kind of to transition into that. I also mentioned that Spectra was a really important aspect of solar data analysis, but at the moment we don't have a kind of a way to support that. And the idea into the future is to provide improved support for data with kind of a spectral axis and multi-dimensional data sets. And again, this might look at NDCube to kind of look at this. We also kind of want to look at a standardized approach to metadata, whether it be time series or whether it be map. So this is something we really need to discuss and to look forward into the future. And then we've kind of, a lot of work has been done to create a package template for affiliated packages. So we kind of want to look at this some further, and potentially this could be an incubator for instrument teams who are interested in getting involved in developing a Python package, but don't know where to start and would like to use SunPy. This is kind of one of the main ideas of these affiliated packages. And one of the kind of really things we want to do looking forward to the future is to grow community involvement. So feedback from users to turn users into contributors. So at the moment, we really don't know. We know an awful lot of people use SunPy when you talk to people at conferences, but there's no good way for us to really know how many people are using SunPy. So we'd really like to foster more into this community involvement, even for users just to give feedback and things like that. So on that note, I would really encourage anyone interested to get involved in the community and contribute. And this doesn't mean you need to be making PRs to the repo. This could be as simple as reporting bugs, saying SunPy is great, saying SunPy is bad. We don't say that, but request new features and examples or ways that we can improve SunPy. Because I mean, it is a community that we're developing it for the solar community, so we would really like more discussion within the solar community and feedback. And just to kind of give my own perspective of this, I used SunPy throughout my entire PhD and never really got involved in the SunPy community for fear of maybe, I don't know, I wasn't good enough to contribute code, or I didn't really know. But I'm so mad at myself that I didn't. And now that I have been involved, it's been such a really great experience. The community is fantastic. I've learned an awful lot. So I would really encourage anybody out there that might be a bit apprehensive about getting involved in the community or reporting issues on GitHub or talking in the Riot channel, like, please do. The community is great, always here to help. And even if you want to say, I want to get involved and don't know how to start, please just come and give us a chat. Or check out our newcomers guide on our documentation website, which is really nice, kind of has a kind of a way of how different ways you can get involved and how to kind of begin with writing code and things like that. So with that, I will finish my talk, and I'm happy to take any questions.
All right, thanks, Laura. That was great. Thanks for kicking off this our hack day. Okay, so I don't see any questions in the talks Q&A channel or in the general channel, but if anyone who is listening in on Jitsi has a question, feel free to speak up.
And if you don't, that's okay. You don't have to ask right now. I mean, I'll be here for the next few days, and yourself will be here, and lots of other people from the SunPy team, if you have any questions.
Yes, yeah, we will all be around. We also have a SunPy matrix channel as well. So we have several, but we have a general one as well. So feel free to jump in there and ask any questions.
Yeah, and I'll put the slides on the SunPy presentations repo, and I will share it on the Slack channel.
Awesome, thank you. Oh, okay. Maybe there is a question. Okay, yeah. So Wan Lu had a good question. I think that's something that we kind of have talked about at the coordination meeting and several other places. He says, do scientists not used to open source find the amount of infrastructure needed to contribute daunting? Things like continuous integration, automated tests, etc., version control, I'm sure.
Yeah, I guess it is a bit intimidating to do that, but I guess I mean, that's when you kind of start to get involved in the community. I think, and having people that can really help you do that, and it doesn't make it a little bit less scary when someone kind of talks you through it. But you're right, it can be intimidating, and I don't really know. I mean, I think SunPy now what we're trying to do is to have kind of like a lead mentor person, so that if someone comes along and you want to get involved, you're essentially given a mentor to kind of guide you through doing that. And I think that things like that are really important to kind of break the ice or to see how this can be done. Or if anybody else has anything to add to that, please do.
Yeah, no, that's a good point. I think adding on to your point about the documentation is that there's been people that have spent quite a bit of time on our docs creating a pretty comprehensive developer guide as well that sort of walks you through these steps of how to set up the kind of various things you need to get going and how to make a contribution.
Yeah, there's always people there to help if you for sure.
There's questions in the YouTube chat box. Okay. So Guillermo has asked, is there support in SunPy for Resi data?
Some at the moment. I mean, there's time series data which can be used within, which supports Resi. However, not yet. We don't have support for things like Resi images. But there's been an awful lot of talk about this, and we're thinking of actually putting it into the now instrument affiliated package, which is SunKit Instruments, I think. I'll send a link that we're going to start developing more kind of Resi specific things there, for sure.
Shelby asks, are there regular meetings for the Plan 2.0 development we can join or listen into?
Yes, I mean, you can get involved in our Wednesday telecons, which is at 5 UTC, if I'm correct. I'm really confused at times. But yes, yep. we'll post a link to that in the PyAstro channel. But yes, there are. We have community development meetings on Wednesdays that anyone can join.
Mm-hmm. Yep.
And we'd love to have you.
So I think our 2.0 release should be coming in the next month or so. I guess I should really know that. So yeah, this is but there'll soon be talks about the kind of 3.0. Well, we've already had talks about the 3.0 roadmap and what will be added there. So yes, if you have ideas, please jump in. Okay, if I'm missing, if anyone has any questions, again, feel free to jump in, or if I missed any in the various chat rooms, please let me know. Questions, again, feel free to jump in, or if I'm okay. Well, if there are no more questions, then I guess we will go ahead and jump right into hacking. So our hacking is scheduled to start officially in 15 minutes, but I don't see any reason to not start earlier. And again, so it's we'll start. We're scheduled to start midnight Dublin time, which is what's this? 2300 UTC. We'll hack for the sort of next 7 hours or so, and then we'll have another set of 2 talks. The first one by Brett Morris, similar to this one, but on the state of the package for the SunPy package. That'll be at 8 UTC, followed by a talk on the SK telescope by Bruno Morgado. And then we'll keep hacking until 2300 UTC. And then a few hours later, we will do the hack presentations. And this is all on the schedule, obviously. So perhaps most importantly in the schedule, there's a column that says sort of what which SOC member is on duty, quote unquote, during that time. And so again, just because of various time zones, some of us will be awake, some of us won't be. So during those spots, this is the point of contact. If you have any questions or concerns about what's going on, how to get some piece of information, if you're having trouble with any of the chats or anything like that. So yeah, feel free to continue hack shopping. It's never too late to add a hack idea or to join a hack either. So don't feel like you've missed your chance or anything like that. And then for people that have ideas, please add them to the spreadsheet, and then create your some sort of room, whether that's Jitsi and Matrix or whatever your preferred method is, where people can get in touch with you and collaborate with you on your hacks. So if I've missed anything, if there's anyone else from the SOC that had anything to add before we adjourn and start our hacking. If there's any last questions from Laura, for Laura. Okay, well, thank you everyone for joining in, and good luck. And again, don't hesitate to get in touch with any of us through various kind of communication channels. Thanks.
Great, thanks, Will.